Bacteriophages, also just simply referred to as phages. These are viruses that infect bacteria. Just like how COVID infects you and me, bacteria can be infected by bacteriophages. So phage therapy, this is where if there is a particular type of bacteria that we want to target, this is typically like a multi-drug resistant, like nasty pathogenic bacteria that someone is infected with. What we would want to do is isolate a bacteriophage or a phage that will specifically kill this particular type of nasty pathogen, and then administer that to the patient. The phage would infect the bacteria, burst it open, clear up the infection, and then the patient will be nice and healthy again. Antimicrobial resistance is going to become a huge problem in the coming years. By 2050, it's going to be killing millions of people unless we can do something about it. So this particular paper, this was led by a very talented student in the lab that I was in previously. This was led by Bhavya. She developed this software pipeline to basically accelerate resolving bacteriophage genomes. So this is a very crucial step in the bacteriophage therapy kind of pipeline. So we need to isolate those phages, assemble their genomes, work out if there's any problematic genetic elements that are in those genomes before actually then giving it to the patient. So this is a significant bottleneck when it comes to phage therapy, because the longer it takes for you to resolve the genome of these bacteriophages that you isolate, and the worse the patient gets. And bacteriophage genomes are typically very small. So if you were interested in isolating and assembling one particular phage that you've just cultured, you wouldn't actually need a supercomputer for that particular step. However, if we want to build up a biobank of bacteriophages and we're doing this at scale, it makes a lot more sense to go down the supercomputing route.